Today I will briefly introduce the bitmap images. Okay, some terminology will be given here. The definition and some background knowledge about the bitmap images. So first is about the resolution. So resolution is a measure of how finely a device transmits continuous images using finite pixels. Okay, so basically in bitmap images, we usually use pixels to describe the resolution of the image. So for example, the resolution of a scanner, they usually use such a metric. For example, here, dots per inch. It means in a small distance, we usually use the inch. For every inch, how many dots? You can treat it as a pixel. But the dot is shown here is pixels on the paper. So for printer or scanner, they usually use the DPI to describe their resolution. And for the video frame or computer monitor, they usually use the pixels dimension. For example, like this, width multiplied with x. Okay, for example, 1,000 by 700. Like this. So the resolution of the digital still cameras is often quoted as the total number of pixels in the largest image. For example, maybe 10 billion. Not much. 10 million. For example, 10 million pixels totally. It can record it in digital camera. The pixel density is assumed to be 72 dpi for the usually used for the screen resolution. Okay, and the bitmap image has pixel dimensions. Okay, but no intrinsic pixel density. So actually, for image or digital image, they just have the pixel dimensions, but they don't have the distance inside it. So the physical size, there is no physical size. The physical size for image, but when it is displayed onto the screen, or you have to print it on the paper, so you have to scale it. So it will depend on the pixel density of the device. Okay, for example, here you see we have these three figures show the device resolution and the image size. So the image size, for example, maybe the image size is 600 by 400 pixels, like this, but it doesn't have the density. So when you print it, when you scale it or display the image into the screen or print it on paper, the size is dependent on the screen or the printer resolution. For example, here, if you use it means the DPI means the dot per inch. Okay, you can treat each dot as a pixel. Okay, so here if the dot per inch is 72. So your image, the size, the actual size of the image will be like this. But for this, if the dots per inch is 600, means I will have 600 dots or 600 pixels in the inch. Okay, so your image will come when you show it on the screen or print it, it will be very small, like this. Okay, because each inch contains 600 pixels or 600 dots. Okay, so it will look much smaller. But for this, it looks much bigger. Okay? Any problems? So they are the same image. All are the same image, but they use a different resolution density to show it out. So you will see they have a different size. Okay? So most image formats we call a resolution. The resolution of all the pixel density together with the image data. So it's usually the resolution of the device are pretty oriented. Okay, here we show two different resolutions. The first one, here is one is 32 dots per inch, and its pixel is very small, right? 198 by 148 and 49. And for this one, you can see the two figures, the two images are of the same size. Their size, I mean their width and the height are the same for the two images. Okay, but this image is the resolution density is 600 dots per inch. So, and its pixels, actually you can see 60, 40, 60, 54, and 1240 pixels. Okay, so when you zoom in the image, you will see this is closer. Okay, very fine. The details are preserved in this image. So although you can see the image size are the same, but due to their different resolution density, it's preserved. For this case, it preserves more details in this image. Okay. And then so scaling an image without changing its resolution, changing its pixel dimension. Okay, it's also the same way to changing the resolution without changing its size. So we saw the previous examples, you can see the relationship between the image's resolution and their size. If you reduce the pixel dimension, we call it downsample. Increase the pixel dimension is called upsample. But both can lead to a loss of quality. Okay, so you see, if you just have, for example, 10 million pixels of your digital photo. If you downsample it into maybe just 1 million, or you upsample into 100 million, it's how to generate the new pixels or how to produce the downsampled images. So basically, it will lead a loss of the quality. So if you want to do such a theory, to up-sampling or down-sampling. You have to apply some image processing technique to do it to smooth, to make the image after you down-sampling or up-sampling, to smooth the image quality. Okay, so interpolation is needed. We will apply some such information, image transform processing techniques. Okay, here is an example. Okay, you can see it's our original image. Now we are going to zoom, scale up the image. So if you scale up the image, you will see the image becomes like this. You just, for example, maybe I just scale up for maybe 1.5 times of the original image. So you can see that each pixel they move. For this one it moves to here. And for this one it moves to here. You just change its location after the scale up, right? So you can see the image will become like this. There are some gaps between them. Okay, so we have to build up this both. Okay, here we use you can see called the reverse mapping. Okay, the reverse mapping is to just map. And just to check how about this pixel. This pixel is gray or I just map it to the original image to fill the hole. Okay? So let's check again. Let's check it again. For example, here is our new image after scaling up. Okay, so how about this pixel? Which color should it be assigned? We do the reverse mapping. You know, we have basically linear transformation, right? So you can find an equation to map this pixel, to find this pixel belong to maybe here, it maybe belong to here. So you can based on the transformation, you will know that this pixel should be drawn with here. Okay, and how about here? For this pixel is almost white, but with a little mix of some gray and the yellow. So use the reverse mapping technique, you will find it belongs to maybe here. So you can fill it with the white color like this. So it's called a reverse mapping. Okay. Okay, so it's the general idea of the reverse mapping, like this. So here is our original image space, and this is our source image after the transformation. Okay, so suppose that you have transformed the original image into this one by no matter you are scaling it up or scale down, down-sampling or up-sampling, no matter what technique you need, you use. And the source image space, for example, you just treat the intersection as a pixel. Okay, so today I want to know for this pixel. So which pixel I want to know the color of the pixel. That's my goal, to know the pixel. So we can use the reverse mapping. Okay, you can refer it to this. Oh, okay. For this pixel, if I reverse map to the original image space, it belongs here. It can be mapped into this position, x1. question is, the XY is not at the pixel location. Okay? It's just this location is inside the 4 pixels. Okay, so here we just treat each intersection as a pixel location. Okay? So you can see from your source image when you reverse map, because I want to know the color. So I just reverse map to the original image. I find it belongs here. It is inside the 4 pixels. So how do you determine its color? If you know the color of XY, you can assign the color to your source image to this pixel UV. Okay, so do you understand my question? 你了解我的问题吗 ？Okay, do you understand? Okay, so it's good. Do you have okay for it? Yes. Okay. So the question is how to find the color. How to know the color value, determine the color value of X, Y. The question is like this. For example, like this, I just want to scale the image into this one. Okay, so it's called a subtemplate. That is scale up and scale down from the original here, the original to our source. So it becomes smaller, right? I just scale just zoom in and I just scale down this image size like this. Okay, so I want to know when I scale down, I want to know for example this one I want to know its color. So how do we generate know its color? Just map effect to its original source. Okay, so for example like this, if I want to know the color here, it's the original image, so fill with the color, each pixel with a different color. Okay, so now I want to know after the scaling down, how about this pixel color? You just use maybe I can use a small one. It would be much easier. Like this. You see, I just held the original image, right? From here to here, I just held the original image. So how about the color? How do you know the color? Just map it. You know, you use the reverse mapping. You know these pixels, the source pixels belong to where? Belong to this, belong to here, right? It's exactly belong to here, right? Okay. But for this point, there are 4 pixels. This point is inside the 4 pixels. So how do we determine this color here in this position? If you know the position of the color, you can assign the color to here to generate the color to show to the on the screen. Okay, so it's our problem. How do you know the color and its position? And this position is not at the pixel. Okay. So maybe the position here we have some different colors like this. Some are black and some are green. So how about the color? You can see at this position there are some pixels are black and some pixels are green. So how about this point? The color should be like somehow maybe the mix of the black and the green. Depends on what the algorithm you use to interpret. Here we will use the interpolation technique to generate the color of this and then assign to this pixel. Okay, so here is just want to explain this. But here is a little different. Here we just retrieve the intersection pixel is located here. Pixel is located in the intersection here. Okay, but the idea is the same. Okay, so there are some widely used technique, interpolation technique. For example, nearest neighbor, bilinear, or bicubic can be used. Okay, so let me explain what's the nearest neighbors. The nearest neighbor interpolation is like this. So here, I want to know the UV color of the source image. So I use the reverse matrix to find the location of the original source of the original image is at xy. So xy is inside the 4 pixels. So then I want to assign the color to the pixel. So for nearest neighbor interpolation, it just assign the nearest pixel to this color. So which one is the nearest neighbor? 1, 2, 3, 4. Which one? It's nearest to this pixel. 1. Right? So the first pixel, the first pixel is nearest to this, to xy. So I just assign the pixel value, the color value of this pixel to the position xy, and this color is also equal to the color assigned to be the UV position. It's called the nearest neighbor. So it's very easy, right? You just assign which one is the nearest. You just need to calculate the 4 pixels distance to the position xy, and you will know which is the nearest neighbor. Then just assign the color value of the nearest neighbor to xy. Then check back to assign the color value to UV, to your source image. Okay, it's called a nearest neighbor. And so it's very simple, but the result is not good enough. So some studies use so people the most widely used is by linear interpolation. By linear interpolation is we use the 4 pixels to interpolate the color of xy. So how to do interpolation? Also very easy. You just calculate the distance, the first 1, 2, 3, 4. There are 4 pixels, right? You just calculate the distance of the 4 pixels to the xy. For example, the first pixel, the distance to xy maybe 1, and for the second maybe 2. For the third, the distance maybe 1.5, and here maybe 3. Okay, so you have the 4 distance, the pixels from the pixels to the xy, then you can just use their weight. If you are near, your weight is higher. Okay, so it's very easy. You can assign this pixel will have a higher weight. And for this pixel, because it's 5 from x1, so the pixel, the color value of this pixel will have the lowest weight. So the weight can be, you can use just a linear combination of the 4 pixels distance. And you use the weight, the weight according to the distance, you can generate the color value of xy. Okay? And got it? 好，有问题需要跟我再讲一次吗？可以吗？可以好，这样子，这些可以吗？可以吗？Okay, so it's called a bilinear interpolation. And you can do it further. We call it bicubic interpolation. It's the same apply we just calculate the distance to the x1, but here we apply higher order interpolation polynomial, to interpolate the color value of y. Okay, so here the nearest neighbor is very tricky, but produce a slow part, and bicubic is slowing, but produce a very good result. Bilinear is in between, so we usually use the bilinear because just achieve a good channel between the quality and the time. Okay, so here is the idea. Okay. Okay, you just explain all the idea as told. So this one just to illustrate the nearest neighbor. You can see there are 4 pixels. Based on your reverse map, you find the position here. You just assign the color of x1 of x as the nearest neighbor. You can see P3. P3 is the nearest. This pixel is the nearest to x. So you just assign the color of x. For here is the bilinear expression. So here we use you see the x here. Here we have a different. You can generate the areas. The areas can be treated as weight. So if the area is larger, means they are closer. So the weight will be the weight of the color for P3 will contribute. It will contribute more weight to generate the color for X. Okay, so you can based on this, you can see here P1 is 5 to X. Okay? So P2 is 5 to X. So you can see P2 it just has a very small. The smallest area means the weight is contributed to the X is small. So it's the idea of the bilinear equation. Okay, here we show the figure. You can see this one is the nearest neighbor. You can see the plot, okay, the artifact, very clear, right? So here this one, middle one is the bilinear, and this one is the best quality bicubic. But basically they are very similar, right? But they are both better, much better than the nearest neighbor. Okay? Yeah. So if, sometimes it's not very clear when I project the content to here, because maybe the resolution of our projector is not very good enough. So you can see much clearer in our slide. Now, interpolation will cause a lot of information. Okay, so I think it's very obvious. Okay, next we will talk about image comparison. Okay, image compression. Okay, we can take a break.